before I start, I often take a selfie of my talks. So do you guys want to be in the selfie? And this time around, I brought my buddy with me who also likes to take a selfie. This is Afrita Cat. She's very excited. She didn't go to Cubana last night, so she's like super hyped. All right, let's all take a selfie. Say hi. All right, good. Let's get on with it with building data products at GitHub. Before we start, I actually wanted to talk about a simple clarification. Data science is such a broad topic, and oftentimes everything falls underneath data science. What I am talking about, usually data science can be composed into two separate things: building data products and decision science. So decision science are the folks that do things around analytics that inform stakeholders in companies. So your CEO wants to know, oh, should I increase the price of this product or something like that? Usually the decision scientists work on those kinds of things. They may or may not ship products. And then there are the other side, that people who build data products. These are usually data scientists, machine learning people who build models and ship their models to production. I am a data products person. I build data products. I ship data products to production. What exactly is a data product? So a data product is a product that relies often on machine learning, relies often on data, becomes better as we get more and more data and it gets more and more precise. That is something called a data product. A very classic data product that all of us use all the time is search. Search is a data product. Google search is a classic one. With more and more data, it gets better, it gets better, it gets better. Another one is Uber. Uber is a data product. There are actually some products that are complete data products that if you took the data element out of it, the product would fall apart. Without machine learning and data and optimization, there is no Uber. There's just nothing else. So those are examples of data products. Before I move forward, I wanted to talk to you guys about something very, very interesting. Many of us rely on this three libraries: NumPy, Matplotlib, and Pandas. Did you know that these three libraries, first of all, they're open source libraries. They're all Python open source libraries. They are hosted and exist on GitHub, and they are maintained by 15 people. So, pretty much, you probably would not have TensorFlow without NumPy. Before NumPy, we had to write everything from scratch in C++, doing tensor arithmetic in C++. I mean, you could do it, but it was very, very painful. When NumPy was created, I think around 10 years ago, it really helped to accelerate the growth of machine learning and especially building data products, because now it's easier to do this linear algebra because you have a package. Matplotlib, we all like it, everybody's plotting everything up and down. I don't even know what we did before Matplotlib. I don't know what we did. We have Matplotlib. And Pandas, oh my God, Pandas makes your life easier. I use Pandas and NumPy every single day. I go back and forth between each of them. Pandas just helps me to see the data in a more pretty form. And then when I actually want to do something with it in the production environment, I move it back to NumPy. Why am I sharing this thing with you? This is like a very major coordination effort. 15 people maintaining and coordinating the activities of, for example, if you think about NumPy, 6 people coordinating the activities of 564 people. So that's just a lot of coordination to do. And these repositories, these open source projects, have lots and lots of issues. Sometimes the issues don't go unaddressed, sometimes people don't create pull requests, and they are always looking for more and more people to participate in the community, to have a shared ownership of the community, and maybe eventually they will all grow up and become more of the maintainers. So it's not just left to 5 people. Maybe 564, out of that 564, 50 will rise up and become maintainers instead of just 5 people. And those maintainers right now, some of them, that is not their full-time job. Some of them have full-time jobs. So they've gone to work, they've come home, and now they have an hour, 2 hours, and they're putting that 2 hours at night to help maintain this library all of us literally rely on. So I hope I've guilt-tripped you guys enough to participate in open source. One of the data products that we built, that my team built and shipped, that I'm going to talk about today, what I'm going to talk about today is a case study of building this data product. So the data product that we built is a recommendation engine, the discovery dashboard. It's that thing right there. So if you have a GitHub account, you log into your GitHub account, you will see this discovery dashboard off to the side, and then you can actually click on it and see, hopefully this works. Now, I don't have to drag this into the window.
You're doing that.
What?
You're getting that. It's coming. Right?
No?
Start right.
Oh, there we go. So here is a live version of Discovery Dashboard. This is a recommendation engine of things that I might like based on my account. So let's actually go through this. The first thing recommended to me is Uber Pyro. And it's recommended to me based on the people that I follow. When I say people that I follow, these are people that I follow on GitHub. Does everybody understand what that means? I use GitHub as a social coding platform. So like people use Facebook or Twitter, I use GitHub also to kind of keep in touch with my friends and see more than what they're doing. I mentor a lot of people and I can't actually talk to these people all the time. But I follow all of them on GitHub. And some people I mentored actively like 4 years ago when they were undergraduate students, and now they've gone on to their fancy jobs. But by following them on GitHub, in the morning I can go through my feed and I can see what all of them are doing. I can see, oh, this person has developed an interest in using this JavaScript library. Oh, interesting. This one is doing this over there, so on and so forth. And then sometimes I drop into their repos, open an issue, and I'm like, hey, I see you're doing this. Have you thought about that? Have you thought about that? So I use GitHub for social coding, and I urge all of you to do the same. Follow me. I want to follow you. Somehow we will figure out how we're going to build that community in Daba so that the conversations we're having here can just persist beyond this conference. So it recommends to me Uber Pyro based on the people I follow. I follow a lot of machine learning people, so that does lots of TensorFlow stuff. So more stuff on TensorFlow that I should use. Interesting, Microsoft VS Code was also recommended to me. So all these are based on people I follow. And if I'm happy about it, I can like it, I'll start it. So that means that I can go back to that repository later and play around with it. Or I can say dismiss, I'm not interested in looking at VS Code. It's not something that matters to me. But I want to go all the way down because there are some recommendations in my feed that are not based on people who I follow, but are based on things that I have started. So for example, this PyTorch, RNN, what is this? This RNN text classification. This is sometimes the recommendation engine, it's kind of crazy. I built this thing. And sometimes it's so good, it's kind of like creepy. Even though I built it. I have been working on building an LSTM, CMS LSTM for the last 2-3 weeks. And boom, another version of it shows up in my recommendation engine. So I can probably just go, well, like actually, I will check that one out and see what the implementation is like. And if I like it, I can just take something from it and continue working on it. So that one is something I'm definitely going to start because I want to go back to it. And something else is now think about that. So this is actually a recommendation on repositories that I viewed. Another LSTM CMS text similarity algorithm. So you can just, and we built this because what we wanted to do was, we wanted to, first of all, help people become more and more participants in open source. So if I'm using things like this and I go to this person's repository, several people are building the same kind of things, right? Two of these people are building the same CMS LSTM. I can go into this repository, maybe I'm working on the code, I see something, or I improve upon the code, then I can open a pull request and extend their code. So it becomes an opportunity for me to help collaborate with them on something that I'm interested in, and I can get onboarded into open source based on my interests. not just somebody guilt-tripping you at a conference that you should do open source. It's much more easier to do open source if it's based on something that you're particularly interested in. So let's drag that back and go back. And if you have any questions, you can ask me questions. So there it is, the discovery dashboard. We shipped that one October last year, and so it's one of our data products that we shipped. Now, when it comes to building these data products all the way back, where do we even start from? This is where you should start from. You should, before you even build anything, before there's anything existing in the world, these are the kind of things you should do. You should have something called like your pre-launch checklist, just to keep yourself sane. The first thing that must happen is your product actually has to work. I know that sounds silly to say, but there's so many times that you have this idea and the product does not work. Or it works in some weird way and you ship it. No, your product actually has to work. It actually has to solve the problem that you think it's solving. Then it actually has to work for the users you have in mind. Sometimes you build a product, you ship it, and it works, but it doesn't actually work for the market segment that you thought it was going to work for. If with the discovery dashboard could be very powerful, and still nobody, it doesn't reach anybody that is going to participate in open source, that product has failed. Even though it's out there, it's no longer serving the purpose. When you launch your product, your users have to feel safe. Because the products we work on rely on data, and oftentimes they rely on user data, our users have to feel safe and secure using the product. You don't want to creep anybody out. You want to make sure that you're GDPR compliant. Beyond GDPR compliance, you actually want to educate your user on which pieces of data is informing the product so they feel a sense of agency around its use. They have to feel in control. They have to be able to decide yes, no, otherwise. So the discovery dashboard, I can say, I like this, I don't like that. And if something is beyond like or don't like or dismiss, they need to find a way to be able to reach us and say, give us feedback and things like that. And this one is very, very important because in North America, we're building this product from San Francisco, but this is a globally based product. We have to think about our users outside of the United States. It's very easy to just not think beyond your national boundaries, but this is a global product. And thinking about users outside of the United States forces you to ask yourself some set of questions that you otherwise might not engage yourself in asking. For example, what happens when a great repository pops up on someone's feed in China and everything is written in English and there's no way for that person to access it? They will still not be able to participate in open source because now there's a language barrier. So if you can do something around translation or something like that, then you can help us do that better. The approach that we kind of take in building data products is a drivetrain approach. This was invented by Jeremy Howard and a couple of colleagues a couple of years ago. This is the thing you do. You define an objective, something you want to solve, you identify the levers, you gather your data, and then you finally build your product. So, in defining your objective, the question you need to ask yourself is, what outcome am I trying to achieve? What are you actually trying to do? For us, our outcome was pretty clear. Increase engagement in open source, defined by opening issues in the repositories of these projects. That was the outcome we were trying to achieve. And we had an evaluation framework to figure out if we've actually achieved that outcome. We have some business metrics that we'll track every day. And if those metrics trend upwards, then we know we're achieving our outcome. And then something in thinking about tracking those business metrics is we have to consider data quality issues in the tracking. So number one, whatever metrics we're going to track requires some data. We have to ask ourselves, does that data already exist in our system? If not, then we need to start logging that data, and maybe we'll then delay the building of the product for maybe 6 months or a year, just to make sure that we're collecting enough event logging data so we can actually validate whether the metrics are right or not. Next thing is, what inputs can we control? So we have our metrics now. What input can we control to actually achieve our goal? And for us, what we could control was what people saw on the dashboard. So that's all we can control. We can put things on their dashboard, and if they see, then we can think maybe some things will happen. What data can we collect? In our case, we weren't really going to collect data because we already had the data, and we just basically use the data that we have on our platform, which is a lot of behavioral data around code. So the pull requests, the stars, the number of the watches, whether a project was forked or not, page views and so on. We have all this behavioral data. We gather the behavioral data, and those are the features that we use in our system that we're going to build a model of. And how do the levers influence the objective? So this is our lever. We're going to show something on your feed. How is that going to influence the objective? The hypothesis was, if users see an open source repository they are interested in, they might use the code, and in so doing, join that open source community. And we actually achieved this so good to the point that the VS Code people reached out to GitHub because they thought that an attack was happening to them. Because for some reason, they just started seeing tons and tons and tons of traffic. And they're wondering, what's going on? What is all this happening? Like, is this some kind of attack? And it wasn't an attack because they realized that their repo was showing up in people's recommendation in their feeds, and those people were engaging with it. So for some repos, it's working like crazy. And so that makes me happy to actually know that people are doing this and it's working for them. So if all those things are clear, you've got your business metrics, you have your data logging, you have everything, what you need to do is build a baseline model. Many times scientists get excited about all the tools in our toolbox. Everybody and their mother wants to run to the most complicated over-the-top model. And that is the last thing you should do. For us, the first rule of machine learning is do not do machine learning. Don't even bother doing machine learning unless the problem actually requires machine learning. Because at the end of the day, we want to solve problems for our users, not just build models because, oh, it's cool. Some problems only require SQL. A few scripts here and there, and boom, we're happy. Some problems just require a little bit of counting this, a little bit of counting that, and you're good. Some problems don't even require SQL at all. It just requires a bit better documentation. Until you're sure your problem actually requires building a model, don't build a model. If you have to build a model, the first thing you do is build a baseline model. Baseline model is something really, really, really simple. Usually just count something. Count something, just count something. Something very, very, very simple. So maybe I can build a very naive model that just counts the number of stars on each repository and ranks them based on how in ascending order, and I turn that into a model and ship that into production. What that does is forces me to figure out my ETL very, very quickly. Majority of the work in deploying and building a data product is on ETL and deployment. 80 to 90% of the work is on that. Around 10% or so is actually building a model. With enough data, and we have a lot of data, with enough data, we can build simple models that achieve amazing results. So that's not where we're spending most of our time. We are spending most of our time on data pipeline. By counting something has to make me go and get the data out of my data warehouse, build an ETL, do a job in Airflow to actually do this all the time, every single day or whatever cadence I want, and push that thing to production. And at GitHub, our machine learning people, we are both machine learning experts, software engineers. We own everything from pipeline to deployment. So it's not just modeling. You have to do everything yourself. So counting something very simple forces you to do those kinds of things, makes you really do the work up front. And also, please feel free to ask me questions. This is not a lecture, this is a conversation. For this repository recommendation, this was an interesting thing. It's like a trial by fire. I joined GitHub back in mid-July, came in, I was like, yes, we're super excited you're here. We're shipping a product in 10 weeks, actually 8 weeks, and you're owning this. Good luck! I was like, what? And oh yeah, you're gonna onboard 2 more people. Good luck, you can do it. I believe in you. I was like, oh God, okay. So I owned the fallback model. The fallback model of our discovery dashboard. And the fallback model is there are many people who use GitHub who don't use it as a social coding platform. How many of you people in the audience do not use GitHub as a social coding platform? So quite a few people don't use GitHub as a social coding platform. In your case, it's going to be hard to do a very good recommendation engine because I don't quite know your interest based on the people you follow. So I need to give you a fallback model. A fallback model based on your behavioral data or maybe the page views you have and different kinds of things. So our recommendation engine is based on a collaborative filtering model, but very strongly influenced by your followers. So if you don't have followers, you have to do something else for you. And the something else for you, we call it a fallback model. What we do is just serve you a mixture of trending and popular repositories. And we're hoping that somewhere in there, we'll be able to touch a little bit of something you like. And so that's how we do the cold start problem. Our cold start problem is we're just going to serve you trending and popular repos, and over time improve following you around with the page view so we can serve you better things. So page views and popular and trending repos. But these are relatively simple models. I don't even call them, I guess they are models because they get better with data, but they're not really learning anything per se. So we built that, forces you to do something very substantial and move that out and put that into production. And then after that, you actually have to deploy your baseline models. You just can't build it, you have to ship it. And there has to be an API endpoint. And another human being calls your API endpoint. And things happen. And the engineering department puts that into a product and they see something. Even if it's something not even good, but it forces you to say, we've actually shipped. Now engineering can take this API endpoint and put it inside the product. Put it inside the bigger products, the github.com. Now we've shipped, and then we can then do all the work of making sure that our model is good, our model is perfect, all the communication has been solved, and then we can just focus more on mathematics and making a more advanced model. Then we build the more sophisticated model only after the baseline model has been deployed. In our case, we build a collaborative filtering model. We move that and the other baseline model, we put them together and we come up with a repository fitness score on top of all of that, because there might be an amazing project that you want to recommend to someone, and because our goal is to get people engaged in open source, we have to do work on community and safety and make sure that the projects are inviting to users. If there's a project that we believe is amazing but has no readmes or anything for people to get started in, it might not be a good one to recommend because they don't even know where to start. If that project does not have people who will get back to you on time, it's not a good one to start. If the community around that project is somewhat hostile to newbies, it's not a good one to start. So you have to figure out all these fitness scores around behavior to be able to achieve your goal. So we do that, we have the fitness scores. We build the jobs in Airflow. We have our deployment environment. We use some AWS instances to do the compute. And for this kind of work, we do a batch training. So we're not doing online training, and we update the training table with the true scores every day or every week. And then that's how we build the model in production. Questions so far? Not one? Okay. Wait, yeah.
Do you guys ever look at like the amount of tools that certain repository gets and like monitor that instead of like the reading behavior or something? Maybe like someone coded something that's so intuitive, like they had comments and stuff, and people don't need the readme file. They'd rather just pull it, and then the code just becomes intuitive.
Our fitness score is a mixture of a lot of different things, like tons of different things that is aggregated together as an indicator of open, safe, environment, inclusive. So it's a bunch of things. But the absence of a readme is a big red flag.
And then another thing is, so how do you differentiate from a person that's just using GitHub as a version control, whereas someone that's actually trying to create an open source to let the community use kind of thing?
Oftentimes, the people who want to do the open source have all this work on documentation and things like that, and their repositories are public. A lot of repositories are private. Often people who just want to do version control, maybe not want to, most of their stuff is private repositories. I have to say all this work was actually done on public repositories. So that's probably like those kinds of things. And a lot of people use GitHub for version control, and they're not really using it as an open source platform. But in the world of machine learning, a lot of people do it for open source, and they have people engaging in their projects and things like that. Yes?
To what extent do you need the services of a behavioral psychologist?
To what extent, he asked, to what extent do you need the services of a behavioral psychologist? If you could get one, that would be amazing. We don't have one, but we have a users research group, which has some expertise in behavioral psychology, but that's not their full expertise. They do user research with people all over the world, and they gather data for us, and that data informs product, and then that gets informed to what gets actually built. Yeah?
You guys typically are using testing frameworks and CI and use that as part of like part of the recommendation. So that obviously something that's got tests or has some sort of like checks and CI checks.
We have not put that as part of the features of recommendation engine, but I like that. That might be the next iteration. Put that in there. Yeah. One more.
When do you calculate the fitness score?
We calculate the fitness score a priori, so we calculate it also daily. We just calculate it daily and we aggregate it over time.
And is that a fitness score for each user per repo?
No, a fitness score for the repository itself.
Okay.
So only repositories that have a certain fitness score get served to people.
Is that fitness score dependent on the user?
No, it's not dependent on the user at all. It's only dependent on the behavior of the persons in the repository, in the open source repository. All right, now I want to give you a little bit of a taste of other things that GitHub is up to. So, GitHub and machine learning. Very interesting things happen in the intersection of those two. So the first one is just around behavioral data, right? Machine learning and code on GitHub is where the sweet spot is. So we have lots and lots of code on our platform. We do a lot of work now on machine learning on code. Learning on code is a new horizon of development, and a very interesting horizon of development. And it has major impact, both economic impact and creative impact for all of our communities. We have a lot of code on our platform. We probably have like the largest cache of like information around people writing code and their code. So we have all this information that we can use to help each other do better work, and also has a massive economic impact for everybody. We use GitHub to build GitHub at GitHub. Majority of all the things I learned is on GitHub. Majority of the models I built are from other GitHub users. We use TensorFlow to build GitHub machine learning. So it's very meta. It's just everything lives in the same small world with the same sets of people. But there are certain challenges around machine learning on code. Basically, most of the work that I do in this area is NLP, but it's a different kind of NLP. And the good thing about coming to Indaba is the world that we live in is the world of languages, machine learning on languages. But the language is programming languages and have sometimes the same characteristics as languages of the African continent. You can think of GitHub as a universe, and then there are all these languages that are spoken in our universe. Some of the most popular ones are Python, Java, JavaScript, Ruby, and then we have this long tail of all these, like around 300 to 500 languages that are spoken in smaller communities. So we kind of have the same dynamics of language distribution and behavior as the African continent, where you may have like the major ones of like English or French, and then there's a long tail. But for us, it's slightly easier because we're using programming languages that are based on grammars that have a very, very defined structure. The challenge for us is that the code having structure, a lot of the natural language processing algorithms and work sometimes migrates to code because there's something called a naturalness hypothesis that kind of holds true. However, code is very, very structured, unlike natural language. And then the interesting thing about code is it is infinite in terms of the tokens that you can use. English has a finite number of words in it. Every year they add another, 2-3 words. What was the word of last year that they added? They always do this thing in December where a new word comes into the dictionary, like selfie or something. But it's like 2 or 3 or 4 words every year. Code does not have that boundary because human beings can create God knows how many variables and different names and things like that. So these are the challenges around doing machine learning on code from the NLP perspective. And on top of that, we have the evolution of this language over time. In our Git graph, we have 10 years worth of data. So GitHub has been around since 2008. 10 years worth of data on Git graph that has been evolving over time. That's a major issue. On top of programming languages, we also have natural language because people use their natural language to talk about the code. The natural languages and the issues, the comments, the pull requests. So we have both different kinds of languages in our data set. We have the communities around those languages. The Ruby community is very different from the JavaScript community, which is very different from the ML community, and all of them have their dialogue and discourse norms. So it's basically like different nations in the worlds in the universe of code, and then we have the networks, how they relate to each other, and how the thing migrates. It gets pushed over here, pulled over there, there's a parking. So this is the gnarly world that we exist in. This is our universe, and that's the universe we do machine learning in. So this is what we look like, with the octocart in the middle. You are your octocart, I have my Afritocat, so maybe this is Afritocat in the middle, and then she's doing things, there are pull requests, she's having chats, and the universe of all her data looks like this. There's a graph you can navigate. From finding one repo, I jump into this LSTM repo, I write an issue there, I go to TensorFlow, I do things like that. So this is what the world looks like. So into the future, some of the interesting things we've been doing. Something we did was deep learning for issue summarization. So when you start off with an issue, I had to go through this last week, building this CMS LSTM. The first on TensorFlow, using the Keras framework, but the first version I saw was from Keras 1.0, and there is a specific function that has been deprecated. This function that helps you to concatenate two networks together, and the documentation is not that good. So it takes me to the issues in the Keras repo, and that issue is very long. And by the time I read through and navigate, started like in 2016, ended in August this year. That's a very long issue. By the time you navigate to the end, only to realize there's still no solution and now the issue is closed. You know, that's like, what? No solution, and it just said, closed. Nobody's dealing with this because we've been talking about it for 2 years. What if there could just be like a nice summarization, not just summarization, also something that just tells me fixed or not fixed, so I can even not even like bother with this thing. So my colleague Hannah was saying, build like a small demo to like demonstrate to us. We could just do this issue summarization using a sequence-to-sequence model. And oh, that's nice, that's fun. let's all play around and see how it works. And so, if this issue body, based on just the first body, placeholder overarching issue to track progress on general UX, it gets summarized down to add more info to the UI. So these are the kinds of things we're going to start shipping, hopefully, if there's enough of an appetite, if we think it's useful for people, to just like summarize down issues and just help you. The whole point is to increase and make sure your workflow as a developer is as seamless as possible, so you can just get on with the business of being creative. Versus, there's so many things we could just automate for you or give you tips to make it easier. So that's one of the things that we are doing. Another one is this, which is our semantic search. This I really, really like a lot. This is Hubot. Hubot is your friendly assistant on GitHub. Do you guys know about Hubot? Well, Hubot is our friend. We send him things, he does things for us. I guess like a chatbot or something, I don't know what you call it, but he does things for you. You can write pieces of code and do things for you, call it from Slack. I don't know why I think Hubot is a he, but he does things. He's just there and does things for you. So you can tell Hubot, maybe you type to Hubot or tell Hubot that you're looking for a function. So you can say things like, like tell Hubot you want this REST API and return the results. And then Hubot can go and find the functions that do those things for you. So you can just this one I'm very excited about because I come from the world of symbolic logic, declarative logic, and I like to think in that way. I was having a conversation with someone yesterday, I think it was Nando, that the way we write programs, the way we even think of writing programs, we think of writing programs based on 20th century norms. I will do this, and then I will do that, and then I will do this. It's very sequential. We're like solving the problem that way, instead of thinking about it as declarative. So one of the challenges is behavior change. A classic example is the way I interact with search and a lot of the tools on my computer is through my fingers. I type things. Why am I still typing when I could just speak? It's much more faster just, hello Google, this. Oh no, I still go to type. The same, we want to do something very similar where you just compose the program together as a bunch of functions and you search for your function. And we have so many versions of the same function on our platform. We have the ones that is the most optimized, the ones that is safe, the one without security vulnerabilities. So there's no reason why you should write that function again if there's a vetted, perfect version of it. We'll rather just, you search for that and we'll serve it to you. So these are the kinds of things we are doing at GitHub, and these are the kinds of data products that we are building. And then now we're going to start shifting towards building data products as a service. We'll build all of these things up, and then you can then get the capacity to take that API and build them into your products. So it will not just be something that is available on github.com, it's something that you can put inside your products and just have the ability to do all this kinds of stuff too. Any questions? Perfect, 34 seconds left.
Thank you so much, Jim. One more round of applause.
Good morning, everyone. So today I'll present a bit our experience trying to build software with AI. The research in AI is going at a really fast speed, but people did not get time to think a lot about how to manage or make sure that this new kind of software is deployed in an efficient way. In software, in classic software, people are working for the last 30 years on formalizing how you could manage a software project. Because local static statistics shows that 70% of software projects or even higher fail for different reasons. Not meeting budget, not meeting specification. So in the early 80s, we started with the waterfall life cycle, which is kind of formalizing a really strict way to develop software that starts with gathering requirements, building specification. Then once everything is correctly defined, we go to the design part. Then we go, once we define the design, technical design, we go to the development and implementation. Then we test, and then we go to the deployment and maintenance. And the problem here is if you have any unexpected issue in one of the phases, this workflow does not take into account fixing this kind of problem that you can encounter during your project. So in nature, we got more iterative way to handle this kind of problem. It's gaining a lot of popularity in software development. One of them is agile development process. And in this kind of approach, we try to get short sprints development, and we iterate continuously until we get the final product. Still, even this approach, people are a bit going back to a more rigid process that mix between the first approach and the second approach, because this kind of approach, this kind of workflows do not scale very well on big teams. If you go beyond 7 developers, you start to have issues with this too fast processes. So we see that AI right now is really taking over the software world. So some people would say, are saying that AI is eating software. And why we see the problem like this? Mainly because in classic software development we focus too much on algorithm and not on data. And all the practical development we have in the last 30, 40 years are oriented to algorithm, like unit test. When you build your unit test, you focus on function or methods, and you try to test it fully, but you don't really focus on stochastic data or data that can vary over time. So you just try to make sure that your algorithm works well in some corner cases, in the general cases. UML, which is Unified Modeling Language, is also oriented to algorithms. So you're designing logic blocks, and we try to model the communication between these logic blocks. Logging frameworks are focused on tracing when your algorithm fails or behaves unexpectedly. So how do you ensure that an AI-based system can be tested correctly? How do you make sure that you design your AI system in a really proper way where you can see a global architecture of this complex system? How you monitor failure and unexpected behavior in your AI system? So I think the industry needs to think about all this problem and this new kind of software paradigm. years ago, Andrej Karpathy from Tesla introduced a new concept called Software 2.0, where he sees that software as neural nets. So you just say weights. Your software will consist just in the weights of your neuron. So it's a bit an extremist approach, but he thinks that at the end, software will be just weights in neural network. That you won't have any kind of logic control around it. So it's a new kind of thinking. And people try to find a way how to tackle this kind of project. One first approach is a bit like the waterfall model for machine learning. Consider this kind of workflow: gathering data, exploring data, you process your data, try to clean it. Once you have proper data, you start building your model, you train it, you evaluate your model, then at a certain time you consider that your model is mature enough, you start tuning its hyperparameters, and then you deploy the model. But as you see, this is too static. If you have any problem in this workflow, it doesn't take into account of the iteration nature of development. So then people try to come with a more flexible approach that have some feedback loops where you can solve the issue that you can have during the development. But this is not enough, because in classic software there's a concept of technical debt. So when you develop a software, at some point you need to go to production as fast as possible. So you will certainly have to take some shortcuts. These shortcuts are taken in a manner that you need, it's like that. You take these shortcuts, and then later, once your product goes to production, you need to go back and fix it. So you need to know that you have taken this shortcut. And the problem with AI is sometimes you have a hidden kind of technical debt. For example, in a recommendation system, you will deploy your recommendation system. So your goal is to identify the link that the user will click on. And so you start to change the links that you show to the user, but you're acting on the behavior of the user. So the model you based that you developed were based on the behavior before you put in place this recommendation system. But once you start putting this recommendation system in production, maybe the behavior of the user will change. But if you don't take into account that, so your first model that you built will drift, and maybe it will not be as good as you planned it to be. So this kind of feedback loop creates a lot of problems. So if you don't know that it's okay to go with the model to production, but you need to identify this kind of problem, and they're not that easy to identify. The second kind of problem that technical debt that you can take AI system is that data changes. So in general, in real life, you develop your model based on some assumption on the reality. For different reasons, operational reasons, change in the business model, your reality can change over time. But you build your model on kind of observation of the business, been done like a year before, 6 months before, that people change their behavior. In manufacturing, your manufacturing line introduces a new machine in the line, so the process changes, these kind of things. And once you deploy your model, you won't see this kind of problem directly. So in classic software, your program just fails. You will have an exception or an error. But in machine learning, the program will continue to work, but with degraded behavior. And maybe you will see the problem 6 months after it occurs. But the problem in what I presented is that we're kind of separating between software and AI, as if it was different. But in reality, when you deploy AI system, it's not just machine learning. At least right now, machine learning doesn't work. It needs classic software environment. And this classic software can handle text distribution of your model over classic machines, handle the interaction with the final user on the front end, collect your data if you have sensors and data all the time. So you need classic software to feed the machine learning system. That's why we came with this kind of a more parallel process where we try to have two workflows in parallel. One is for managing classic software. One is for managing the machine learning model. And the main take here is that we introduced a phase that is integration between the software and the classic software and the machine learning phase. So you can test your model without integrating it in your software ecosystem that you will deploy. You can test there's like in classic software, you just finish your development and you start testing. But here, you may test your model in a simulated environment or Jupyter notebooks or whatever. But then, you need also to make sure that you automate you test it once it's interacting with the rest of the system. So now that we defined a workflow for managing our software, we need to decide what to do afterwards. So first thing, we need to build a team for developing this software. But we usually define a data scientist like a superhero who masters everything. Computer science, math and statistics, business. But you must admit that it's really difficult to find someone who's that good in all these fields. So what we advocate is that you need to build multidisciplinary teams. Because data scientists alone really achieve deployable product. We see a lot of AI startups founded by really talented AI engineers but then they struggle to get a viable product or successful product to market because they are just data scientists without software people to help them to deploy, without business people, without system, without graphic designer to UX designer to build a system that is usable by the end user. So if you don't build a multidisciplinary team, you will have a lot of trouble deploying your system. For example, in Instant Yield, we have graphic designers, we have software engineers, we have marketing, and business development, AI researcher, AI engineers. So, and without all these people, we can create products to production. So once you build your team, your first task is to collect as much data as possible. So people start to consider data more valuable than oil right now. We see that companies that are data-oriented are surpassing oil corporations in the stock market. So once you start a project, first focus and obsession needs to be to gather as much data as possible. Even if you think that the data you are collecting is not useful right now, maybe in 6 months or 1 year you will find it useful. Because if in a year you find out that you need this data, you will need another year to collect it. So as soon as you start collecting the data, you build your data wealth. And you can accelerate this process, especially if you're collecting it from user behavior or machines that are loading sending sensor data. You need time to build that. So if you start collecting it as soon as possible, you will see the value of this like later in your project. Then you need also to define metrics for the quality of your data. When you collect data, one of the main problems is you will have missing values, you will have some aberration in your data. So, and it's not usually simple to identify this kind of problem. So, especially if you don't really know your data from the beginning. You have a new customer, you're not necessarily an expert in this field. So you may make some assumption based on common sense, but like after deploying the product, you find that the value of one sensor is not really means that the sensor is failing or something like that. So you need to spend time with your customer, show them the data, get his feedback, so to understand what are the limits that you need to put in. Then, once you collect it, you define your metrics, you need to spend time exploring it. This is really a common error. Like, as a data scientist, the sexy job is to build the model. But normally, you spend 80% of your time cleaning and analyzing your data. If you rush too fast to develop your model, you're certainly not have a good model, because you will try to solve a problem that doesn't exist. So you really need to spend time in exploring your data. You will have pressure to deliver because of the marketing guy promised the client something to deliver in a month, and you will see the clock ticking. So you would say to yourself, go, I take my chance, I'm super smart, I develop the model. But if you go like that, you have like 80% of chance to. Then, we still starting developing it. This is really, we learned it the hard way. So, before even once you have your data, spend time building and automating your data processing pipeline. Because in machine learning, you will have to do a lot of experiments. And if each time you need to put in place these experiments by hand, you will lose a lot of time. And time is money. So it may seem like a waste of time at the beginning of the project. And it's not that easy to put in place this system, these kind of things. But by fully automating your training, your process, your data collection, the evaluation process, you make sure that when you change something in your model, you'll be able to test it quite quickly, and you can iterate faster. Make sure that you don't have data leaks, you're using the right labels, sometimes maybe you load the labels in the correct way. So all these details are important. You can have just one detail, you forget about one detail, and you will spend a month thinking that you have a good model, and at the end you find out that your model doesn't work. So automate your pipeline and invest in it. It's like building your home, so you can't get it in one day. And start with really stupid model, so to validate that your pipeline is working. So don't focus on the accuracy or some kind of metrics. Just build something that's more or less working, and focus on making your pipeline. So now we start building our model. So before even focusing on just the machine learning model, you need to have a big picture of your system. So it's not just software. You need to decide where you will introduce machine learning in your system. Some client comes to you, he wants to solve a problem. So you may say that I will use machine learning for his main core problem. But usually you will find other blocks in your software system that need machine learning. So you have to identify these blocks and put in place a process to develop machine learning. Another thing is we usually in machine learning fan of really the latest machine learning model that is doing SOTA. But in real life, you do not necessarily need that. So you will gain most of the performance from spending time on your data doing feature engineering. In the 60s, I like this metaphor because in the 60s, in Formula 1, people were focusing on improving engines. So it costs a lot of money. They spent years developing that. But then one guy came up in the 60s and said, I can get performance cheaper by using aerodynamics. So, and he developed this famous car, which is the Lotus, that won a lot of championship in the 60s. And feature engineering is like aerodynamics. So it's a cheap way to gain performance. Sometimes the difference between the state-of-the-art model and the classic model is not that big. So you should invest more time in understanding your data and tuning it. You also, when you design in your software, you will identify blocks that are really complex heuristics. One way to get rid of these complex heuristics is to replace them by machine learning. You can even use them as training if you have legacy system to replace. You can use this legacy, these heuristics as a supervised way to train your machine learning. And it's easier to maintain this kind of machine learning model than a really complex heuristics. So once you decide what to do in your system, you need also to plan for monitoring. And this needs to be done from the beginning of the implementation. In classic algorithmic software, you just take a paper, you design your algorithm, and then you go and you implement. So if you have a bug, so you look at your design and you try to identify where the behavior of the algorithm is not correct. In machine learning, you can do it. Your only way to debug is by monitoring as much as possible your model. And this can be in training or in deployment. And the cool thing is that TensorFlow provides you a really useful tool called TensorBoard that allow you to monitor whatever you want in your machine learning and for quite cheap price. It's not like you don't have to do a lot of plumbing to extract metrics. In a few minutes you can just get the distribution of your variable during training. You can have histograms, you can have some cool 3D visualization of TSME projection or things like that. And once you deployed your model, you also need to keep monitoring your model, because otherwise you will have a lot of problems. In developing your model, you should, before even starting writing, you should first identify the class of problems you're trying to solve. Is it classification, binary classification? Is it multi-class classification? You have unbalanced data? Are you trying to do regression? Whatever. So putting a name on the problem you're trying to solve will help you a lot. First, because once you put a name, you can have all the state-of-the-art model of the solution for this problem, and you can reuse them easily. Second thing when you're trying to build your model is to get a baseline. If you don't have a benchmark, you'll not be able to know if you're doing great or not. So get the most simple model, the most reliable one, implement it before going to more complex models, and keep this all the time during your design, so you can benchmark your model. Define a simple objective for your problem. When you talk to clients, in general, they want everything. They list 10 metrics at a time. If you try to target them from the beginning, or to target all of them from the beginning, you'll not get any one of these performance metrics. So try to have from at the beginning. Yes.
Hi. What do you mean by attributable?
So that you can define. Sometimes the client will express something qualitatively. So if you don't have some kind of metrics to measure your progress, it can be like a categorical metric, but you need to put a number to track your performance. If you just say, if your client say this is good, this is bad, that's it, it doesn't give you an objective way to assess. You want to be able to train. So putting one objective at a time would help you a lot in progressing. So once you tackle the most important one, you can tackle the second one. If you target all of them at the same time, it will be very difficult to get your system deployed. Then, so one of the important advices that I give you here is use source control. Data scientists love Jupyter, but the problem with Jupyter is that you can't track your code. So, Jupyter is cool for doing prototyping, experimenting, but once you start building the real model and go into production, please use standard Python code and put it in version control, because you will need this to be able to reproduce your experiments. In training, try to reuse your code between training and test and serving. This will reduce a lot of bugs, so you don't have to fix bugs twice. Separate your data properly. This can be tricky sometimes, because you will usually have to work with temporal dependency, time series. You learn when you begin machine learning that you need to split your data between test and training in a random way. But if you do that with temporal dependency, you will have data leaks. So sometimes the leaks are really subtle, and you need to spend time to see if you just split them randomly, you are creating leaks or not. And keep measuring all the time the skew between your training performance and your serving performance. Because if your data shifts, you will see this shift in this skew. So if you put a number on it at the beginning of the deployment, when you see that this skew is shifting too much, it means that you need to retrain your then use as much as possible mature tools, and you have a lot of them, especially with TensorFlow. First, one of the most important or hidden secrets in deep learning is that in production you never use pre-training, you never retrain a model from scratch. You usually use transfer learning. So you take a model that was already trained, and then you retrain it a bit on your own. It's not worth it to retrain a system from scratch. It's cheaper to retrain a model. To structure your model, use TF estimation. This improved a lot the quality of the code we produce. Like initially, we were building models without this kind of structure, so everyone was coming with his own way to manage the model class. And then when estimators were introduced to TensorFlow, it helped us a lot to have clean code. Use TF data. This is really important for your performance. GPU are really sensitive to the way you load your data, and making sure that you're loading the data as fast as possible for the GPU is not an easy task. But TensorFlow has done the work for us, so you can easily get really good performance by just using this framework. And the final maybe advice is keep an eye on TensorFlow like X extended, because it's kind of an ecosystem for your pipeline. It's not mature enough for, all the blocks are not mature enough for production, but it's already, it can be already useful on some blocks, and I think in a year it will be really the way to go for deploying and managing your AI-oriented software. So if we want to summarize the key ideas that we get from our experience in deploying machine learning software, so try to use machine learning when classic software is complex. Then start with simple model and then try to make it more and more complex. Encourage collaboration between AI engineers, data scientists, and software designers, UX designers, because at the end you're building a software and not just a machine learning. Get your model to production as soon as possible and measure your performance and monitor it all the time, and so you can feed your feedback loop for improving it and deploy continuously. And invest in your data pipeline. This is really important. Thank you for and any questions?
Yeah, cool. So I wanted to start off my talk by saying that I am suffering from massive imposter syndrome at the moment. I mean, I'm excited to be talking to you guys, but I've spoken to so many smart people here that I almost feel like I shouldn't be speaking to you guys. Okay, cool. So the topic of my talk is deep learning in production. So when I started off my slides, I had one slide on architecture and why architecture is important for deep learning in production. And then I had another slide on infrastructure and why infrastructure is important for deep learning in production. And then I had 2 slides in 40 minutes. So I decided to change my topic slightly. I'm going to be mostly talking to you guys about how do you do time series analysis and how do you use deep learning in dynamical systems. And then I'm also going to be talking to you guys a little bit at the end about architecture and infrastructure, but it's just 2 slides. Alright, cool. So just a few disclaimers. One is that the ideas in this talk are pretty generic, and I'm hoping that they might be applicable to other interesting time series, like neuroscience. So if you're trying to detect real-time fits and seizures and epilepsy, that kind of stuff. Cardiology, early detection and warning systems of heart arrhythmias, so heart attacks. Seismology, earthquake warning systems, and actually Google Brain recently did some research on aftershock prediction, so I think maybe this stuff would be useful for that as well. Ecology, so habitat destruction and climate change is also a dynamical, it's also a dynamical system. Epidemiology, this is something that I'm actually quite interested in. I'll be turning it down a bit. Okay, right. This is okay. Okay, cool. Epidemiology is also really interesting, so that's like virus containment and prediction. So if we're talking about like viruses like the Ebola virus, West Nile virus, that kind of stuff, I'm hoping that this stuff can be useful for that. And then obviously finance, which is my background. So we use this kind of stuff for investment management. So whenever people hear this, they ask me a lot of questions about how good deep learning is at predicting the stock market, and this is what I tell everybody. The market does not care how smart you are or your models, and it's incredibly hard. So like our best models are probably getting about 60% accuracies, and that depends on the period you look at. Okay, cool. So with the disclaimers out of the way, let's talk about some fun stuff. So first, I just wanted to talk a little bit about our company and some of the kind of like stats that we have. So we started out in like 2015, and we really just started with kind of like one model in production. It wasn't even a deep learning model. It was incredibly simplistic, and over time we've been able to actually go and scale and implement more interesting models. So now we have about 95 different types of models that we can use, and that extends far beyond deep learning models. So it's your traditional kind of like recurrent neural networks, but also Gaussian process models, regression trees, your k-nearest neighbor, regressors, all those kind of techniques. Also the state space models, which are traditionally used in time series analysis, like ARIMA and GARCH and those kind of systems. The number of model instances, or like actual models in production, I don't have an exact count, but like I said, we started off with 2015, now we've got well more than 1,000 deep neural networks actually running in production at the moment. Yeah, so I don't have an exact count, but I think it's probably closer to 2,000 at the moment. And they produce a lot of data, about 200 gigs of results a week. The total time series which we were processing when we started out, we were processing about 50 time series. Now we're processing 345,000 time series. I tried to explain this to somebody the other day, we got a little bit confused. These are 345 independent time series with many, hundreds or tens of thousands of data points each. So in total, it's many, many billions of data points that we're actually processing. Single instance runtime. So if we had to run our models on one computer, when we started out, it was like a 15-minute thing, very quick. And now it actually takes 40 days per market that we're looking at. So we're looking at a number of different markets. So obviously it takes a really long time. If we run it on one computer, it would take about half a year to build all the models up to where they are now. But we don't run it on one computer, so it's not so bad. Okay, cool. So what are some of the algorithmic challenges that we face in trying to use deep learning algorithms for time series analysis and for stock market prediction? So the first thing we need to recognize is that we're in an online learning setting. So we're continuously getting data as we're moving forward through time, and our models actually need to adapt to changing environments and continue to learn. So online machine learning involves learning from data that arrives through time. So this is how that looks. We have data arriving, we break it up into different time series subsequences, we feed that into some model, and then that model generates out-of-time predictions of what's actually going to happen next. We do next point kind of prediction, we also do sequence-to-sequence modeling, and we do classification as well. We'll talk a little bit about that later. So there are kind of like two different frameworks, or three different frameworks that you can use in kind of like online learning. One is where you get one pattern at a time. We don't generally do that. That's called streaming. That's quite common if you're working on embedded devices or something where you have very little processing power. Sometimes you only get one pattern at a time and you need to actually build your model on that. What we generally do is kind of like online batch learning. So we have some amount of historical data which we're fitting our model on when we're walking forward through time. Cool. So already at this stage, a number of questions are starting to arise. So one is, how do I prevent having to learn everything from scratch as I walk forward through time? The next thing is, how do I know that my model is actually learning? Alright, so let's say you train a model and walking it forward through time. How do you know that it's actually learning? It's actually adapting to change, which is the entire premise of online learning. And how much or large or frequent should pretty much everything be? So your training versus your inference frequency, like how often should you update your models? Things like window sizes, how much data should I be training my model on to generate the best sample predictions, etc. Alright, cool. So the first thing is, how do we transfer information through time? So the nice thing about neural networks, which you don't necessarily get if you're working with decision trees, is that you can actually just transfer your weights from one point in time to the next. Keep getting messages. Right, cool. So weight transfer. So basically, what we're going to do is we're actually just going to transfer our weights from time t to time t plus w, where w is our window size. So we'll have our weights. This time we'll say that as like a numpy array. We'll transfer that into the model at the next point in time, and that'll actually be the initial weights that we start with when we're learning. So what that allows, I'm going to actually do this one. When people are asking me how much I'll point, it's like, there's a good answer. Okay. Right, cool. So we're moving our weights through time. Okay, so there are a number of challenges with this, which I'm going to talk about later. So this approach actually biases the model to historical data, because you're continuously learning on some amount of data. You're basically upsampling the historical data in this setting. So there's something that you need to do. When it comes to actually making sure that your models are actually learning, something that we've been looking at recently is actually studying the dynamics of the neural network. So how you can kind of think of training a neural network as a very high-dimensional random walk. So we have our weight matrix, and maybe it's like 10, 20 million parameters, and this thing is actually going to move around in this parameter space, and the amount that it's moving around is going to tell us if it's actually learning, right? So to test whether our models are actually learning, we're going to look at the dynamics in the weight matrices through time. So basically it's exactly the same picture, except that at each point in time what we're going to do is we're going to drop both of these weight matrices into some distance function, which is going to tell us how much this neural network has actually learned. And that's going to basically answer the question of how do we know that our model is not just stuck and it's actually continuing to learn, right? But there's some challenges with this. If you are trying to measure the distance between a model with like 25 million parameters and most of them are 0, it's hard. So we have to look at some different kinds of distance metrics. So one of the things is we tried the simple kind of distance metrics, you clear distances between these matrices through time. That's not great. But also you can measure the distance between the singular values of your weight matrices through time and or the norm of your matrices. And you can also measure the distance between the principal components which you extract from each weight matrix. So let's look at some real data. This is the only slide which has like real data. If you guys want to look at other data, I've got tons in this computer. So I'm going to talk a little bit about errors and uncertainties just now. But this is a graph of basically the out-of-time error of our models in a simulation from 1998 to, I think, last week. And also the uncertainty of the model. So how certain is the model in its predictions, and it's been standardized so that it should be roughly normal, but you can see classic finance, it's not normal. So that spike in the middle is actually 2008. The spike kind of on the left is 2001, and now we want to ask ourselves the question, well, did our neural networks actually learn in these regime shifts, like when we went from one world to another world? So these are actually the neural network dynamics layer by layer through time, and we can see that the neural networks do actually learn in 2008 during the financial crisis how to kind of like adapt to change. So this is a reassuring graph for me. It tells me that these neural networks are actually able to adapt. Whether they're able to adapt quick enough and whether they're able to learn something that actually helps them rather than hurts them is obviously still to be decided in the future. One thing that's really interesting about this graph though is just how much learning happened in 2016, right? So we can kind of think of the model as learning a model of the world, right? So it learns what the world is, right? And when the world changes, we experience errors in our models. So if the model has to change a lot, then that tells you that the world is changing, right? So here, what we're looking at on the right-hand side is literally how much are our weights moving. I think this is the PCA, distance measure, I'm not sure. But we see that it moves a lot in 2016, but we see that there aren't a lot of errors in 2016, which tells me that maybe the neural networks were able to adapt without experiencing errors, which is really like a holy grail, which is like you go through a regime shift, but your model kind of preempts it and is able to adapt before you experience massive out-of-time errors. Cool, the next thing which I said the question arises is, how do you select the values for the models? So one of the easiest ways is really just to do ensembling or stacking. So what we do is we create a whole bunch of different neural networks with different parameters, and we can blend them together. Either we can feed their predictions into another neural network that learns when to use what parameters, or we can do some sort of voting system, where the best model historically, or the most certain model, gets the highest votes, and we can kind of blend these predictions. But my favorite approach, and something that I'm quite inspired by after David Silver's talk yesterday to do a little bit more work on, is to actually kind of wrap up all of our agents as reinforcement learning agents. So this is something that we do, which is every single thing we build into our framework is a reinforcement learning agent. It's up to you whether you want to learn with the reinforcement learning agent or not. So how that looks is we will have our RL agent, and this is basically a controller for our supervised learners. And what it's going to do is it's going to try some random stuff. In our neural network, it's going to set some parameters, it's going to change some things, and then this whole thing is going to walk forward through time. We're going to measure the reward, we're going to reward the reinforcement learning agent for the decisions that it made, and then we're going to try some more random stuff. So that's kind of the principle behind reinforcement learning. Obviously, it's a little bit more sophisticated than just trying random stuff. You've got a distribution which tells you what is good stuff to try and what is bad stuff to try. You guys can ask questions while I'm talking, by the way. Don't have to wait till the end. Alright, here we go. Okay, I'm going to talk about features. I think it might be in this section actually. Cool. Okay.
How do you validate your models with respect to the time series data?
How do we validate it?
Yes, evaluate it. Yeah.
Oh, evaluate it. Yeah, so there's a lot of different metrics that we'll look at. So if we're doing regression, we'll look at your standard kind of mean squared errors and your mean absolute errors and all of those kind of things through time. So our test set is actually the data that comes after the point in which we train it, right? But we've also kind of done some interesting work on other metrics. So in our case, what we're trying to do is we're trying to generally predict a whole bunch of stocks, and if we just took the mean squared error across the errors in those predictions, we would actually be weighting all of those stocks equally. But in reality, some stocks are more important than others. Like, we're talking about the JSE, if I get the prediction of Nasdaq wrong, that's a much bigger deal than if I get the prediction of Woolworths wrong. Because I generally have a much higher weight in my portfolios assigned to Nasdaq because it's very liquid. So what we've also looked at is actually doing different weighting metrics across the errors of all of the different time series that we're predicting, and using that as our kind of validation. Cool, so pattern matching. Alright, cool, so I'm just going to introduce some of the challenges with doing pattern matching and time series analysis. So one of the things that's often overlooked is that time series occur over different frequencies, so there are different time scales, and there are also different magnitudes, like stochastic volatility and these kind of things. So in this situation, we have a very similar graph to earlier, except that we've got this very similar pattern, just has different heights. So that's an example of different magnitudes. Now, if these patterns occur quicker or slower, then it would be an example of the same pattern occurring over different time scales. So given this, we need to ask ourselves a few questions. So how are we going to adjust our data to deal with different magnitudes? And this gets back to the question of the features which we're extracting. And is it possible to learn features across multiple time scales in a standardized way? Cool. So time series pre-processing techniques. So we basically look at mostly 3 different ways. We'll do rolling standardizations of our data. So we're going to walk forward through time, and we can use some amount of data to compute a mean, some amount of data to compute a standard deviation, and we'll convert it into some sort of z-score. And we can then feed that into our models. You can do the same thing with normalization, which is where we're taking it between a value between 0 and 1. We can also look at the differences in our time series. So we can say, instead of looking at the stock price, we're going to go and actually look at the percentage differences or the logarithmic returns of that time series through time. Another thing that you can do is you can convert it into categorical variables. So I'm going to say something which some of you might disagree with, but that's cool. Basically, a time series, or like a continuous random variable, is kind of like a categorical random variable where you have an infinite number of bins and you have massive class imbalance, right? So one of the things that people do when they're trying to predict time series is they say, all right, well, instead of treating this as a regression problem, where we've got like an infinite number of possible outcomes, it's treated as a classification problem. So how we do that is we basically discretize our continuous distribution into number of bins. So now you see what I'm saying about how you have massive class imbalance. So let's say we went from this continuous kind of distribution at the top to this one at the bottom. Almost all of our data is actually sitting right in the middle. And the reason why that happens is because when we're doing our bins, we're taking equal distances in the value space, right? As opposed to taking equal with bins in the probability space. So something that we found works quite well is instead to do it this way around. So we're going to actually build bins which are equally likely to occur, but where the magnitude of the values in each bin has vary a lot. So these are the resulting bins that we get from this kind of procedure. So over here we have massive class imbalance, and our model is typically going to learn to just predict what it is in that bin. Over here we're giving it classes with kind of like equal probability, so it's going to learn something a little bit more interesting. But the challenge with that is there's a very, very wide range of values in some of the bins that are around the edges. I'm going to get that question out. But generally in finance, at least, that's okay. Because I don't really care, exactly how much my stress is going to go. I care if it's going to do nothing, if it's going to go up a little bit, if it's going to go down a little bit, if it's going to go up a hell of a lot, or down a hell of a lot. Like, those are the things I really care about. So this actually answers that question in a way that doesn't bias our models. Yes?
It's the left-hand side, is that similar to like the variance over a running mean, or of the
left-hand side?
Yes, it's the bins, the Gaussian-like distribution.
Yeah.
Okay.
Yeah, so basically if you're taking, for example, not the prices of the stocks, but you're taking the returns of the stocks. Generally, that's like logging the industry.
Okay.
Anyway, it's got fat tails, so it's not quite a nice Gaussian curve like this. This is just simulated data to like demonstrate the idea. But you can still, the cool thing about this procedure is you can actually do it on any distribution. So in finance we have very high kurtosis, and we've got these fat tails and massive outliers. So using this procedure we actually are able to construct equal sized bins for our time series or any kind of empirical distribution. I don't know if that answers the question.
No.
Alright, cool, so that's, yeah.
Sorry, two questions.
Yeah.
Firstly, what do you do if the underlying distributions aren't stationary? Do you use an online distribution?
Everything that I'm showing is online. So, like every single transformation we do is done in an online setting using some amount of historical data.
The second one was, do you differentially bias it to get interesting results? So you said, like, you really want to know if customers goes up a lot, down a lot.
Yeah.
You want to know that more than if it went on the time.
Yeah. Yeah, I mean, there's like, the thing is that there are biases in either approach. In this approach, what we're going to end up with is a model that's pretty much predicting the mean, because that's the most likely kind of outcome, and it's basically a trend following strategy. It's not very interesting, and it's probably going to lose money. Right? In this one over here, at least we're giving the model a shot as to whether or not it is going to actually learn something that you can make money off of. Is like
Well, you meant just you give it, could you bias, say, for maybe one of the largest more complex model famous bird?
Yeah, I think you can like do something in the middle as well. Sorry, I've got quite a few slides to go through. I'm running out of time. Okay, cool. So better distance metrics. Another problem is time scale. So you can have exactly the same time series but occur over two different time scales. If you measure the distance between these two time series using Euclidean distance, it's going to tell you that they're totally different. They're not totally different, they're exactly the same. So one of the procedures that you can use is something called dynamic time warping. It's an old school technique. It's been used in signal processing and voice recognition for many, many years. And basically what you do is you drop your 2 time series onto this distance matrix, and then you use a procedure to basically fill in the distances between the different points along the time series, and you measure the distance between them as kind of like a really shortest path between the top right corner and the bottom left. I'm not going to go into details on how you calculate it. There's a great Wikipedia page on it, so maybe go and check that out. Regime shifts. So this is actually the thing which I'm most interested in. Most of the time, this is what happens. We're training our model on some time series of sequences, and everything is going great, and then all of a sudden, the world changes. Oh, you guys can't see it. It's like really dark. Anyway, there's some red lines over there, and they're going down. All right. So instead of up. All right. So we've experienced some sort of regime shift at this point in time. And the reason why I showed the predictions in gray is because when we can kind of think of a regime shift as going from the distribution that our model has been trained on to some other distribution. You can also think of it as going from an interpolation kind of phase to an extrapolation kind of phase. So a few questions we need to think about here is, have regime shifts actually occurred in blocks? Like, does this actually apply to you? So in finance, we know that regime shifts occur every time Trump tweets. So I don't have to worry about testing that. But if you're working with time series analysis in another domain, maybe apply some of the statistical tests to see if there are actually like unit roots in your time series, and if you do experience outliers and significant changes in your distribution. And then, if they do occur, is there a way that we can actually estimate the likelihood of them occurring? Okay, cool. And then when transferring data through time, so when transferring the knowledge that we've learned in the past into the future, is there a way that we can transfer just the relevant information or adjust it in such a way that our model can adapt to regime changes quicker? Cool. So out of time errors, I've mentioned this a few times. It's a very simple concept. We have some predictions, and then we see the real world, and then you're probably not going to see it because it's all in red, but basically we measure the distance between these 2 time series, and we can do the squared or the absolute distances, and that's actually what I refer to as out of time errors. Yeah. So these are known as residuals, and they contain a lot of really, really useful information. So don't throw your residuals away when you're doing time series analysis. One is just like before you even deploy them into production, just looking at your residuals and doing a randomness test on whether or not they follow some sort of random walk is very useful, because if they don't follow a random walk, then you know that your model hasn't learned everything from the time series data. Right? Because if your model has exploited all the information in the time series you gave it, there should be nothing left in the residuals to make it non-random. Yeah. If you guys are interested in that, my blog is basically all about randomness tests for time series. Secondly, models learn a representation of the world. Right? Like I said earlier, they learn a world, and then if the world changes, we're going to see errors in our models. Because the model has kind of like approximated what the world is, and if the world changes, we see errors. So it can actually be a very useful kind of like indicator of whether or not we're currently experiencing a regime change. But this is backward looking, because we're looking at historical predictions. So I'm going to talk about forward-looking estimations of regime shift as well. Lastly, the error terms can be used to reinforce behavior and attributes in our models. So we can actually use the error terms in our reinforcement learning loop to make our models more certain or less likely to have errors by picking better attributes. Cool, so estimating model certainty. This is something which I've spent quite a bit of time on. But certainty, this is the definition I laid out, so it's probably wrong. But certainty is the likelihood of our model making a similar or the same prediction given an input sequence which is insignificantly different. So high uncertainty patterns generally correspond to patterns outside of the distribution of what we've trained on. So when we present our model with a pattern and our model says, hey, I don't know what to do, that generally means that that's actually outside of the distribution of what we trained our model on. So how can we go about measuring that? So what we can do is we can randomly apply dropout at inference time and actually sample different predictions from our model. And you can kind of think of this as actually sampling predictions from subgraphs in your computational graph and building up a distribution of your predictions. So if you do that for a pattern which is inside of the distribution, you're going to get a very certain result, or hopefully. If you start doing this on data which is actually outside of the regime, you might end up with very, very wide predictions when you do that. And that's actually a very uncertain. So maybe now, if our models are extremely uncertain, we're actually experiencing a regime shift. So we move from one distribution to a new distribution. So that graph I showed earlier, the errors and uncertainties, this is basically that. So there are a few different ways that you can actually measure uncertainty in your models. So the first is you can add noise layers. So basically what these things do is add a tiny little perturbation, a little bit of noise onto your input patterns, and that allows you to sample predictions on patterns which are very, very similar to one another. The other thing is to actually use dropout at inference time. So generally we train our models with dropout, but we don't use it when we make our predictions. I'm saying do that. Actually use dropout when you make your predictions, and don't make one prediction, make like 200 predictions of what's going to happen in the future. And then draw a distribution of all of the different possible predictions and use the variance in that distribution as a measure of your model's confidence in its prediction, right? Another thing is switching off entire pathways. If you have different feature extraction channels that are in your network, you can actually say, all right, switch off this channel, let's get some predictions, switch off that channel, let's get some predictions. And then also you can add probabilistic layers. So TensorFlow probability has been released recently. I'm not using it in production at the moment because I don't think it's very stable. But they have a whole bunch of additional layers which you can use, which automatically add variational inference to your models. Cool. And another cool benefit of actually measuring our uncertainty and our errors is that we can do some really interesting things with sample weighting. So sample weighting is a way of saying these patterns are more important than these other patterns, right? So if we train our model, we're walking forward through time and we've identified a number of highly uncertain patterns, when we get to those patterns at the next point in time, we can say, actually these patterns are really important because the version of your model from 3 months ago really struggled with this. So pay more attention to this when you're making your predictions. So that's basically like sampling your data in proportion to the certainty of it. So we pay more attention to stuff that our model got wrong in the past, and more important, and we pay more attention to stuff where it wasn't sure what was going on in the past. So this generally works quite well, and it's also quite useful if your regime shifts are very low probability events, and you don't have a lot of data where you're uncertain. Cool. Another thing, noisy transfer learning. So previously we were talking about how we have our weights. Yeah.
What do you do if your model was very certain that it was actually being wrong?
Now that's a really good question. That's a great question. So the question is, what do you do if your model was really certain but it was totally wrong? So it really screwed up. What we have done in the past is we've blended sample weights together. So we've actually said, take the maximum of the sample weights. So we'll compute sample weights for the error terms and sample weights for the uncertainties, and take the maximum sample weights and feed that into the model. I haven't had many situations where, so in my situation, the error terms and the uncertainties have generally been quite correlated. So I haven't seen much change, but I'd like to kind of study situations like that because that's really interesting. Okay, cool. But yeah, you can definitely just average out your sample weight. So noisy transfer learning. If we're experiencing a regime shift, a lot of the stuff which is being encoded or embedded into our neural network weights is not going to be relevant for the next point in time. So what do we do? The one thing that we've been playing around with is actually passing this through a noising function. Again, with the red, it's a little bit hard to see, but there's a little n over there for like normal distribution. You don't actually add normal noise to it, but I don't know how else to represent a probability distribution. Now, there are some challenges with this, so caveats. Don't ever add noise to a batch normal layer. You're going to end up in some weird parameter space, and your model is just never going to learn again. So generally only apply this to feature extraction layers, and something that we've been doing is, well, if we have a function which returns the probability or likelihood of a regime shift occurring, then what we can do is we can reinitialize weights from deepest to shallowest. Because you can kind of think of a neural network as doing high fidelity feature extraction through the layers. So the features extracted in the first layers are generally general time invariant things of time series, like there exists volatility, and the ones right at the end are very localized to this point in time. So when we experience a regime shift, the information that's not very relevant is the stuff right at the end. So what we can do is reinitialize a number of weights going from deepest to shallowest, and actually allow a model to, it's basically brain damage, right? We're going to hit you on the head with a hammer, and hopefully you'll learn things quicker. All right. Then we apply the distance metrics again. Like I said, don't add too much noise. And also do it on a layer by layer approach, because don't add noise too professional. It's a bad idea. Temporal transfer learning. So this is something I've been playing around with recently, and this is the idea that what if you're in a system where you actually experience similar regimes over and over again? So in financial markets, we have bull markets, we have bear markets, and we experience financial crashes many times. So maybe in 2008, instead of just transferring the weight from the previous month and adding some randomness to it, why don't we go back in time and find weights that were useful and transfer that into our model? So what we do is we have our function, which tells us, it's basically an early warning system. It says, listen, we're likely to be entering into a regime shift. What we're going to do is we're going to go backwards in time, find a point in time where the weights are actually quite good on the training set that we have now, and then load that. So maybe we'll do that from like 2001 to 2008. We can also allow it to not transfer weights. So if it doesn't find any weights that are useful, just reinitialize the model, learn completely from scratch. Obviously that will affect runtime, but yeah. So in this situation, it's actually transferred weights from further back because it reckons that these weights are better than those weights for transferring. So it's a very simple thing to do, but we've seen some interesting behavior where it actually picks weights from many years ago when it's trying to make predictions during these kind of like high uncertainty periods. All right, I don't have a lot of time left, so I'm going to go quite quickly through this. Most of the time, we're not interested in univariate time series prediction, and this is when neural networks are awesome because many of the traditional kind of like state-based time series analysis tools are strictly for univariate time series. You can't feed in a lot of like exogenous variables. So how can we actually deal with multiple time series which have a very rich and interesting covariance structure? And how do we deal with collinearity as well? Like let's say I'm feeding all of the stock market returns into my model. Many of those stocks are driven by the same forces, so they're going to be very correlated. And what you can get in that situation is that if you can construct another time series, it's just a linear combination of the other ones, you can end up with collinearity in your earliest feature extraction layers. So one of the ideas we had was, well, why don't we do time series embeddings? So basically, what we're going to do is we're going to take our multivariate time series and we're going to embed it in a space which is lower dimensional and hopefully has better statistical properties for prediction, and then decode from that space back into the original space. So you can do this with PCA, ICA, FCA, but you can also do it with something cooler like an autoencoder. So in this situation, we have all of our inputs going into an autoencoder, and they're all in their own individual channels. I'll explain why in like 2 minutes. And what we do is we encode that data into a lower dimensional latent representation, and then we decode back into the original space. So how that looks is we have our multivariate time series coming into our model. We reduce the dimensionality. It produces another time series, which is of lower dimension and of better statistical property. And then we predict in that space, and then we use the decoder to get back to the predictions that we actually wanted in the first place. So I highly recommend this approach. It's also very computationally effective. You don't have to have as big models. You can scale. It works well. Cool. This is probably the stuff that is the least successful stuff that we've worked on, but it's interesting. Yeah. Yes, that works really well. Yeah. Some of the other ideas are presented earlier, but that one I'll tell you. Interpretability issues. Why does interpretability matter? Okay, first of all, if you can't interpret your model, you have no idea what edge cases are. You have no idea when you should expect model failure. And models fail all the time. Don't think that your model, once you put it in production, is going to perform half as good as you think. It's going to fail. The only question is, are you going to be able to work out when it's going to fail? And are you going to know why it failed? Right. So we want to understand what conditions would cause model failure. We want to know what input variables the human being in the loop needs to pay attention to. We also want to know how we might be able to improve the model going forward. And interpretability is also a massive roadblock for many real-world applications where humans have a legal right to interpretation of the decisions made. Also, whoever solves this problem wins a journalist. Yeah, so, right, cool. Ablation studies. I'm going to do this really quick. I got like 60 seconds. All right, so basically ablation studies, very simple, is the idea of if we randomly switch parts of our neural network off and then on again, and we evaluate it on our validation set, we can actually work out what matters. So in this situation, we have our inputs, and this is why we do all of our different time series coming into the model in their own independent channels. We have some model. So over here, what we have is we have two feature extraction channels. Maybe one is an LSTM, maybe one is like a dilated convolutional neural network. And then we have our multiple outputs, which we're predicting. And what we're going to do is we're going to switch off the first input feature extraction channel. So what we're going to do there is we're basically just going to zero out the whole rate matrix. And then what we do is we measure the performance for each one of the outputs on the validation set. We do that again for the second inputs feature extraction channel, another one for the third one, another one for the fourth one. And what it tells us is which inputs are most important to which outputs, right? Because if the model deteriorated a lot, we know that that was important to that output. Another idea is neural network distillation, so that's Anna's research up there. You can chat to him afterwards, I have no idea what's going on. But basically, neural networks fit a very complex function of your data. It's generally nonlinear, highly uninterpretable. The idea is very simple. Can we use an interpretable model, a linear model or something, to actually try and mimic the decision boundaries of this other model? So what we do here is we basically fit a decision tree to not fit the data, but to fit the model. So we train a decision tree to try and predict what the neural network is going to do, and then we look at the decision tree to try and understand the neural network. So it's kind of like an interpreter. This hasn't worked super well so far, but there's a lot of people doing research on this, including Hinton, and we published something last year on this. Okay, I told you I had 2 slides on architecture and infrastructure. They're really quick. Right, architecture matters. Imagine doing deep learning without a deep learning framework. Yeah, it's a total, like, you would literally spend 5 years just getting the dropout working. Alright, so don't just pay attention to the maths and the stats. Pay attention to how you're building your code. Pay attention to code reuse and good design principles like object orientation, testing, and infrastructure. So how our infrastructure actually works these days is we have a directed acyclic graph, which is all of our different reinforcement learning agents, within which we can have different supervised and unsupervised learning models, and we basically play with Lego, we put them together, and we get them to collectively solve very complex tasks. So a good architecture is something which takes the bottleneck from kind of like producing the code to test an idea to actually testing the idea. Now, good infrastructure is something which makes testing of ideas really easy. So infrastructure also matters a lot. The good news is that infrastructure has gotten a hell of a lot easier to do. Originally, we kind of had everything running on a computer. These days, what we do is we have Docker containers running on multiple instances, and what we do is we drop each one of our agents onto different instances, depending on whether it's GPU or CPU bound, and then we kind of aggregate the results at the end. The cool news here is that it's gotten a hell of a lot easier with Amazon Web Services, Google Cloud Platform, Docker, Docker Compose, Kubernetes. All of these tools are out there. They're kind of like black magic, but you're good. Well, that's it.